Welcome to Linear Methods. After completing this lesson, we should be able to understand the Pipelines API for logistic regression and linear least squares, perform classification with logistic regression, perform regression with linear least squares, and use regularization with both methods. The Pipelines API also provides models for logistic regression and linear least squares. Both models use an implementation of ElasticNet to provide regularization. ElasticNet is a convex combination of L1 and L2 regularization terms. If its parameter alpha is set to 0, it is equivalent to a ridge regression, and if its parameter alpha is set to 1, it is equivalent to the lasso. Let's start with the logistic regression. It is widely used to predict binary responses, that is, for binary classification problems. Its ElasticNet parameter is denoted as alpha, while its regularization parameter is denoted as lambda. The logistic regression can also be generalized into a multinomial logistic regression. In the case if there are k possible outcomes, one outcome is chosen as pivot, and the other k-1 outcomes are separately regressed against the pivot outcome. The benefits of logistic regression are that it has no tuning parameters, and its prediction equation is simple and easy to implement. MLlib's implementation of a multinomial logistic regression, the first class 0 is chosen as the pivot class. Then its output contains k-1 binary logistic regression models regressed against the pivot class. So, for a new data point, these k-1 models are run and the class with the largest probability is chosen as the predicted class. Two algorithms are supported in MLlib's implementation, a mini-batch gradient descent and LBFGS, which is recommended for faster convergence. In the fight against overfitting, researchers during the 90s proposed different ways to penalise large parameters. This is called regularization. Spark's linear regression implementation supports different types of regularization, L1 or lasso and L2 or ridge regression. The combination of the two is called ElasticNet. And if there is no regularization term, it is a simple case of ordinary least squares. This is a formula table showing how the ElasticNet is combined with both the L1 lasso and L2 ridge regression smoothing techniques. There are two parameters, alpha and lambda, corresponding to the lasso and ridge regression smoothing techniques. If you haven't downloaded the dataset from the previous lesson, there is a link in the script to download it to your temporary folder and load it. Now we look at an example of binary classification using logistic regression. First, I create a new instance of a logistic regression and set its parameters, maximum number of iterations, regularization, and ElasticNet parameters. Then I call the fit method to produce a trained model, which I name log_r_model. Notice that I'm still using the training data from the original data frame I have randomly splitted in the beginning of this entire module. I can then inspect the weights, coefficients, and the intercept of the trained model using the corresponding attributes in a model instance. Moreover, I can access the logistic regression training summary object through the summary attribute of the model instance. This summary has plenty of useful information. For instance, the objective history, that is the error of the model in every iteration. The summary can also be used to evaluate the model. This is the topic of the last lesson of this module. Now it's time to introduce linear least squares, the most common formulation for regression problems where the average loss equals the mean squared error. It also supports different types of regularization, both the L1, lasso, and L2, ridge regression. And if there's no regularization term, it's just a simple case of ordinary least squares. Here's the example of a linear regression. I create a new instance of linear regression And just like I did with logistic regression, I set its parameters, number of iterations, regularization, and elastic net parameters. Everything else goes exactly the same, fitting the model, inspecting its weights and intercept. Also accessing the summary of the linear regression, I can observe the objective history, that is, the error of the model in every iteration. Let's explore this summary a little bit further this time. Besides the objective history, which I have introduced before, I can also get all residuals in a data frame by accessing its residuals attribute. This is an example of the residuals for the first 3 elements in the dataset. After completing this lesson, we should now be able to understand the Pipelines API for logistic regression and linear least squares, perform classification with logistic regression, perform regression with linear least squares, and use regularization with both methods.